Welcome to a lesson with Dr. Powell. Let's take a look at a related rates problem situation or scenario. Let's suppose on a triangle we know that the perimeter of this triangle should be kept the same, maybe like say 10 units of some kind. Also suppose that we want this angle right here, which I'm going to label as beta, to be the same, to be constant. So it's not going to be changing, so where it's going to be held, you could write this as d beta dt is going to be equal to 0. Another way of saying it's going to be a constant, and we're going to let that be not only instantaneous but the whole time. A plus b plus c equaling 10. If you were to think of this as a function equivalence, the constant function 10 is equal to these side lengths added together. No matter how a, b, and c are changing, the sum of these functions as functions of time, of t, is going to be always the same thing. Then with this function equivalence, then the derivative of this function 0 is going to be equal to the derivative of the sum of the functions. So you could think of this as being dA dt plus dB dt plus dC dt is equal to 0. We might use that. Okay, so now let's think, if we knew some information about this triangle, if we knew what maybe like dB dt was and dC dt was, then we could figure out what dA dt was from this equation. That's kind of nice. But what if we wanted to figure out like what dA dt is and dC dt and dB dt was, or maybe we have some more things to figure out that we don't really know particularly at this moment in time. Now, if you looked at my previous couple videos, we had something called function equivalence that we take to a derivative equivalence. A little practice with this, all right? Let's try to come up, this video is mainly just practice coming up with function and derivative equivalence equations. And you could apply this to various situations when you have specific numbers that you can plug in to find out what you're looking for. But this is just practice with coming up with function equivalences and derivative equivalences in a situation like this. Namely, the perimeter is going to be constant, so we know that. But also, maybe we have an angle, right, that is going to not be changing. Let's come up with an equation of the function equivalence equation that relates the sides a, b, and c together, but maybe using beta as much as possible because we know it's constant. That's kind of nice for derivative sake, right? Okay, so we can think in particular, see this triangle right here. I like this triangle, this little triangle in here, even though it doesn't have a beta. Let's see how we can use beta to talk about the sides of this triangle. Then maybe we could do a Pythagorean theorem right here on this triangle off to the side. So this side right here, you could think of it as being c times the sine of beta. Thinking in the unit circle, if this side length instead of being c were 1, then this, of course, would be sine of beta, but then just rescale by multiplying all sides of the triangle by c, so c and then c sine beta. Okay, so this side length is c sine beta. That's nice. What about this one right here? Well, before we answer that, what about this one? We know the full length is a, and maybe we'll just erase it so it doesn't get confusing for a minute. The full length across is a, but maybe we want to figure out specifically, and actually we can use beta to talk about this side length. Just like this side, this is c sine beta. This right here is c cosine beta. So what would this be? Wouldn't it just be a minus c times cosine beta? So we could right here just say, okay, a minus c cosine beta. Then we have a nice Pythagorean theorem right here. We could have, say, something like c sine beta quantity squared plus a minus c cosine beta quantity squared is equal to b squared. That's a function equivalence, and then you can take a derivative of that and work with it. Now, are there other ways of coming up with a function equivalence equation that we could work with? Yeah, but I was trying to use the idea here, how can we just use one of the angles only, right? Okay, so in particular, it's going to be a constant. Sine beta is a constant. Cosine beta is a constant. So that's going to be handy when we take a derivative here and when we look at it. Now, a kind of a note in this particular situation, if we get like something like 2c sine beta using the power rule, then multiply by the derivative of the inside, which is c times, hey, beta's constant, so a constant, c times a constant. So that would just be dc dt times that constant. This part right here is the derivative of the inside, and this is just the inside, the inside itself, but then multiplied by 2, right, because power rule. Now notice you have a sine beta times sine beta. That's sine beta squared. So this really looks like 2c dc dt, and then I'll put a sine beta squared right here. Then here you can think of, okay, you take a derivative of this using chain rule. That would be what? 2a minus c cosine of beta. Then you have to multiply by the derivative of the inside of this, which is dA dt. Remember, cosine beta is a constant because beta is a constant. Because you're plugging in a constant into a function, your output a constant. Great. So dA dt minus dc dt times that constant, which is cosine of beta. Yeah. Then you have some foiling to do right here. Now, it might be useful to notice, well, we'll just walk through it. 2 is going to be multiplied to every single thing here as we move along. So the first is, I just read it here, plus 2a dA dt, so I just used the f of the FOIL. The outside would be plus, well, actually minus, right? Let's see, 2, right. So the outside would be with the minus right there. So minus 2a times that dc dt cosine beta, inside's right here with the 2, minus 2c cosine beta dA dt, and then the last, something interesting here, you get plus 2 because you have a minus, and then you have a 2, so plus 2, and then you get c dc dt cosine squared beta. Notice you have this times sine squared beta, and the same thing times cosine squared beta. If you factor out of both of them, you get a sine squared plus a cosine squared. They both have the same input, beta. I mean, that's going to be 1. On the unit circle, Pythagorean theorem, on the unit circle, hypotenuse is always 1. So cosine squared plus sine squared better be 1, right? Okay, so that's nice. So really, those two terms get swallowed up in just simply 2c dc dt. And then you have the rest of the bit. Of course, we just took the derivative of this one side. On the other side, so then you could write down the rest of this, just this right here, put it down here. And then that would be, and then that would, of course, be equal to 2b dB dt. And of course, depending on the situation, how the question is asked, what is dA dt, dB dt, dC dt, or whatever else you're looking for, this might be a nice way to go. Specifically, where we're only focusing on the sides anyway. how the different sides growing or not growing, whatever else. And we're using the fact that d beta dt was 0, so that was the only angle that really came up. So we never had to multiply by d beta dt at all because d beta dt is 0, right? So if we did a product rule or something, or some kind of chain rule with it, that part where we have d beta dt coming out, which is 0 out anyway, so we can just basically pretend that it's a constant the whole time. Okay, so that was just a little example of how you can build function equivalences and derivative equivalences. Please look at the last 2 videos. This is just kind of commentary on the last 2. Something else that we can do with triangles and related rates. Thanks for watching.